The first one by Detlef. Oh, please wake up. It's your talk, Characterization of an IMX291 video camera in the lab. And then followed by Michael on a similar topic. Detlef, stage is yours.
Okay, good afternoon, everybody. Good morning, actually, right? It's still in the morning. I'm time shifted. Okay, we changed the title a bit. I just said IMX-based camera. And this is the camera we looked at, which is what we currently use in our All-Sky 7 camera systems that we have available in Munich. And we are interested in photometry, so I'll talk a bit about what photometry really is. So we want to understand the behavior of the All-Sky 7 camera, but it's not only All-Sky 7. It's basically any of these cheap Chinese cameras. Are they suitable to do proper photometric work? And in the end, you know, we think something is possible. You get larger errors than if you have a professional scientific camera, but of course they are 10 or even more times more expensive. So we just want to present you in a set of 2 talks what we were doing in this respect. Why do you want to do photometry? We have really a science project in Munich where Michael is working on as part of his PhD thesis to better understand the flux density of small asteroids / large meteoroids. That's paid by ESA's Planetary Defense Program. They're interested in understanding better how many of these small impactors do we really have, because they could pose a threat to assets on our planet. That's number one. The second one, which might be of interest to many of you, in particular those that look for meteorites. Of course, the luminosity, and we heard this yesterday also from you there, is important to understand the mass of the object. So you, for example, the end mass, if you look at the path of the fireball, you want to have a feeling for the mass that ends up on the ground. You really want to have good photometry. You want to understand the energy that was emitted by this object. So that's really why you want to have good photometry. Now, this is a graph I showed last year, just as a reminder. So if you're interested what we are doing in terms of these flux density measurements, this is a result from cameras that we had on Tenerife for very small objects, like these were intensified video cameras. So the brightest object we had in the small field of view was like 1 magnitude, and it goes down to 5th or 6th magnitude. That fits the flux density, so that the number of objects per square meter and second fits very well the Grün model, which is kind of a standard since many years in this business. But okay, not too much details on that. The other one that I mentioned briefly, meteoroid end mass. There are a number of methods to determine the behavior of an entering meteoroid into the atmosphere. And like Mankricevich developed this method, which is used in many of the papers that were already cited. And it's a parameterized thing. And the 2 parameters here, those of you that worked with this will recognize it. This mu here, that contains information that you get from absolutely calibrated photometry, from the information how much light, how much energy is really emitted in form of light. So that's why it's important. Now, proper photometry needs proper calibration. This is how it's done. If you want to get the real information in the image, there's 2 effects. One is that you have something we call the dark current, or also for video cameras, the readout noise, which is sort of mixed together here somehow. Actually, these cameras we see later are dominated indeed still by dark current. So when the temperature changes, you change the dark current. What is that? It's signal that's generated by thermal noise. So even if you have a completely black image, you know, you cover your camera. I have a black towel that I put over the camera. I switch off the light. We're sitting in the basement and we do it at night. So it's as dark as it can be. And you still get a signal, all right? It's because of temperature that generates electrons in your detector, and that looks like light, which it's not. So you have to subtract that. And then the next thing is you have this effect that if you go to the edge of the field of view, the image typically looks darker, right? So there's two things there. It could be vignetting from your lens. It is simple geometry in addition, because as you go further away, in particular for large field of views, the light is spread out over more pixels. That's something you can correct by taking a flat field. A flat field means you image a evenly illuminated surface, where if you do, like if you look at the wall here and you put a light on it, you can generate an evenly illuminated surface. It's not as easy as that, because if you have a large field of view, then because of the geometry, because of the different angles you look at, again, it's not really a flat field anymore. I'll tell you how we deal with this, and then Michael will show you some details. And the other thing I noted here, in particular for these cameras, which are color cameras, we also need to somehow take into account how do the three different color channels, red, green, and blue, behave. We have two things. This is also something I think we presented last year or even 2 years ago. We built a Meteor simulator where we have a box with LEDs, with a pinhole. It generates light. We can calibrate that simply by comparing the signal with stars. In the meantime, we have calibrated detectors where we can do the same thing. And the camera, we take an individual camera, one of these Sony something cameras, and we have it on a turntable so we can simulate the movement with different angular velocities. And this is then how the image looks like. So basically we put the light box somewhere at the end of the corridor. You have to be far enough away that your pinhole really is just smaller than 1 pixel. And then you can simulate by turning the camera an apparent movement of the light curve. And you see this kind of trail here. These are effects that come from the compression algorithm, which we're trying to really quantify and understand in detail here. But I want to talk more about the dark images and the behavior of the camera as a function of temperature. And this is our optics lab, which we installed after Christmas, was a Christmas present, which Michael organized for us. There was some money left over, which we had to spend within 10 days. The hardware had to be in the office 10 days from the order. And Michael managed to do that, so we bought all sorts of fancy toys. One of them is an integrating sphere. Inside it's spherical, and it has a light source at the side. And now because it's spherical, even if you have a larger field of view, it always sees the same brightness, okay? And Michael will show you a flat field. This is where we switched on for the first time an LED. And we have calibrated sensors, at least for another 10 months they are calibrated. Then we need to redo the calibration where we can really measure the number of photons per second. This is how a typical dark image of one of these IMX cameras looks like. It's stretched, right? And you see, well, first thing you see is green. You see these pixels. They have a name. I think they were called macro pixels or something. I forgot the name. This is part of the compression algorithm that always thinks in terms of pixels. Macro blocks, yeah, exactly. Thanks. That's what it was. You also see there's more signal at the bottom for some reason. And the rest, it looks really cool. It looks very homogeneous. That's only because there's a processor behind it. For comparison, this is a raw image from another camera that I'm working on that will go to Mars, hopefully in the year 2028. And that's how a real dark image looks like. You can basically see differences in every pixel. You see a broken column here where something is different. You see the gradient from the right to the left. This is all gone, and it should also be there in this image, but it's just all this processing power that sort of flattens this, because of course the goal of these cameras is to produce nice images which always give you a good image no matter what the light condition is. So how do we deal with this? Well, just to understand in the lab how these detectors work, the first thing I always do is I put it in a dark room, as I said before, and I change the temperature. And what you expect is as the temperature increases, you get more signal. And you see that nicely here. Okay, this is number of frame. I have plots later where I show you this with respect to temperature. But of course, what happens, the camera starts at 25 degrees centigrade, room temperature, or 22. If you put the towel over it, you switch it on, it slowly heats up. And in the end, you have something like 45 to 50 degrees. And that's what you see, is what you expect. As it heats up, the dark current rises, but then bloop, suddenly it goes back down again. It rises, goes back down, it rises, and so on. Because it has all these automated things, automatic gain control, backlight correction, and whatnot. So this is, of course, changing also the photometry. Okay, here the values go from 38.5 to 40.5. So you could say it's not that much, but the same thing will happen if you have this illuminated. So to do proper correction of these images, we should not have these switches. And we're currently trying to understand this, playing with the settings of the camera. What can we switch off? Here's the same picture now as a function of temperature for the 3 different color channels. And here you actually see that for the blue and the red, it increases as we expect. The level of the green is completely different and it does not increase. So you change the color balance as a function of temperature. That's why you had so much trouble to do the color correction, because it's a function of temperature. So this is something we need to consider. Okay, now we try to switch off everything and suddenly it looks much nicer. This is now, for some reason, I still don't understand why this now is scaled from 0 to 1. We have to look into this a bit more, but now it looks much better. As a function of temperature, it increases. There's this bump here, which also I don't understand yet, but it's fine because now I have a curve that I can use for correction. It's much better than this switching that we had before. So I think we're going in the right direction here. And I just discussed this with Sirko. I have the camera that should go to the Bavarian forest. I cannot install it because of construction work at the house. We'll first put it in the lab with Michael to do some flat fields in the lab. Then we'll mount it next to the other camera I have in the Netherlands. And then we run one with fixed settings and the other one with the standard settings. And then we see whether it makes sense to change some of the settings of these cameras. Here's a different one. Again, automatic gain is off, but still we set the exposure time not to this 1/50, which is a fixed value, but we let it jump, but we said, okay, you are allowed to change between 50 milliseconds and 50 milliseconds. Where I would think it should just stay for 50 milliseconds. But again, you get this strange behavior that it goes up and then it jumps back down. Okay, here we missed some data. So this is what we want to avoid, to do proper photometry. And by checking the settings, I think we can improve the current photometry. We can definitely, in the end, when we're done, give some estimates on the errors. If it's just 0.2 magnitudes or so, then maybe it's not so bad. But with the current settings, what we said is good photometry is challenging. Already the dark current is difficult to predict. Behavior depends on time. For the light images, it depends on illumination. I don't know whether anybody looked at images, for example, from fireworks during New Year's Eve. The detector actually changes on this macro block level, the gain settings. So you cannot say, okay, if the gain changes, I have some stars in the image, so they're also changed. That might not be true, because it might keep 90% of the image normal, and only where you have the really bright part, it changes something on this macro block level. So this is something which I think we need to understand a bit better. And this proposal, I think we start already looking into it. And in an internal discussion in the All Sky team, we were also pointed to an open source firmware that you could upload to the camera, which hopefully somebody will look into. For your information, all these different settings that you have, I put in the appendix here in the PowerPoint, and with some explanations of what it actually is, all these terms, because I didn't know, I know what BLC means, but then there's W something, blah, blah, blah. So for your reference, I just put it all there. You can all look this up on Wikipedia yourself, but I found it convenient to have it as part of this presentation. So that's the first part, and then Michael will go a bit more in detail into real sky measurements and also these flat fields. Thank you very much.
Thank you, Detlef. Before we come to Michael, time for questions. He's the first speaker who actually saved 30 seconds.
You lose it with the questions.
Hi, Detlef. Question, usually people actually advise to, to switch off automatic gain and so on. So your results show it for the All Sky 7. The question is, should we worry about all the results coming from All Sky 7, or should we worry for all the results taken for the past 20 years?
No, definitely not. I mean, the first thing is the astrometry that you get is not affected. This is really the details of the photometry. And as I said, you will see figures from Michael. If you have images of Vega, then say the pixel sum over a number of pixels in his aperture changes from 2,500 to 3,500. If you work that out, that's something like 0.3 magnitudes. So I'm not sure whether we need to worry. That was not the intention of this talk. The intention of this talk was to say this is already a fantastic system, in particular if you look at the price, but we are hoping that we can improve the results. That's the only thing I'm saying here. Okay.
More questions?
Mike.
I just wanted to have a follow-up question or comment about Jeremy's question in that we do these settings the way that we do them because they're optimized for fireballs. And if you turn all this stuff, like in black and white, if you're optimized for dim meteors, your fireballs are going to be bloomed out. And that's just my preference. That's my philosophy. And it really ultimately, we leave it up to the individual operator of how they want to configure their settings. But you can either have the dim meteors optimized or the fireballs optimized. That's just my philosophy on it.
Thanks.
All right.
So then, let's thank Detlef again.